All right, well, we're trying a little experiment here. I'm going to try to record the whole screen as I go here. This microphone isn't very good on this webcam, which I don't love, but I want to look at the worksheet as I draw some diagrams. So I guess I could have printed it out and done it, but I figured I'd give this a shot to see how this goes for this one video. I don't like the video quality over here, but anyhow. All right, so this worksheet, this recap of Newton's laws, right? We had this in class, kind of collecting up some of the stuff we've done in class and compiling it in one location. So an object at rest or in constant velocity motion will stay at rest or constant velocity motion unless an unbalanced force acts on it. So that's you give a bowling ball a push, it rolls across the classroom. It doesn't need a force to continue to propel it. The unbalanced force was when you pushed it, and that got it up to a velocity and it kept rolling. The constant velocity motion, you can have that bowling ball can roll and move whatever. It's a terrible bowling ball. Let's say something's moving. Let's say it's frictionless, right? So it's got a bunch of wheels or something. I don't know. It's moving at a constant velocity, right? This is its velocity. Well, it has a bunch of forces acting on it, right? It's got the normal force from the ground, all right? It's got force of gravity. Now the normal force, all right, normal means perpendicular. The perpendicular force here acts on the bottom of this surface of this object. It's the force of the ground on the object. We call it normal force. The word normal means perpendicular to, so we just call it Fn when it's a ground. Now, we'll see something in a minute here about how we label that. So the normal force is always perpendicular to the surface. Anytime two objects are in contact, the force of contact is perpendicular to the surface of contact. But I will say the thing you have to watch out for here is when we label it normal force, we're labeling it normal force when it's in contact with a ground or desk or a flat surface like that. If it's two objects touching, which we'll see in this worksheet and the questions, we label it a little bit differently. So this object could have forces acting on it, but as long as they're balanced, it'll move at a constant velocity. Now, when I give it a push, maybe this is the force while I'm pushing it, force of the push, that's going to accelerate. Now, if it's in a situation where you're pushing it and it's going at a constant speed, then that means there must be a force resisting that motion. And it's usually force of friction, which is our next lab we'll talk about the force of friction. Now, the next one, an object's acceleration is directly proportional. A is directly proportional to the net force. F net is a way to say total force, all right? For instance, if you pulled something to the right with 10 newtons of force and you pulled something to the left with negative 5 newtons of force, F net would be positive 5 newtons. Whatever's left over, once you cancel out, find the difference between the forces. So F net, another way to say it, is the sum of the forces, the total force. And it would be plus 10 newtons plus a negative 5 newtons equals positive 5 newtons. Now, in a situation where, oh, that's great. In a situation where the forces are balanced, F net equals 0 newtons. That means everything's balanced. So the acceleration, because it's proportional to F net, would be 0. And inversely proportional to object's mass. And it's not just proportional, it's actually defined as that. Acceleration is equal to the net force divided by the mass. So the net force acting on the object divided by the object's mass. All right. And the third law, for every force acting on an object, there's a force acting on another object, equal in magnitude and opposite in direction. Now, this is what this worksheet really gets down to trying to work on, to identify. Newton's third law, we call that. And we have a little example in class where We pull two spring scales, a string between them, and no matter what we do, the spring scales always read the same quantity. No matter what we do, it's two spring scales, so it's like you take two little scales and you connect them by a string, and we pull on, right? Even if one person tries to quote unquote pull harder than the other, they both read the same amount. The contact force between them is always the same. So this problem here, why you are not falling through the floor. Okay, there's the ground holding you up, the chair holding you up. An inanimate object such as a table exert a force. Can the magnitude of force be exerted by an inanimate object change? Explain and give an example. Well, of course, a table can apply a force, and it can change because you can apply a greater force to it. Now, in class, we talked about this, but for full remote students, right? If you put something heavy on a table, right, the normal force acts on it. All right, holds it up. If you put something twice as heavy on the table, the normal force is twice as much. All right. So the table responds. The normal force is a responsive force. All right. It responds to the force that's applied down on it. All right. So the FG of the box is pushing down on the table. The force of the box is pushing down on the table. So the FG of the table, if that gets bigger, then the normal force has to respond by getting bigger to keep everything balanced. Now, how does a table do that? Well, any solid you can draw on a macroscopic level, a molecular level. Pretend these are the molecules that make up the desk, right? And here's like the surface of the desk. What we do is we model all solids as little spheres representing the molecules connected by springs, right? Those are springs, like in a box spring almost, like a bed. All right. So imagine you put something on a bed, right? You lay down at night to go to sleep. The bed sinks in and supports you. Now, the more massive you are, the heavier you are, the more that bed will sink to support you. So what happens is these molecules, right? You set something on it, they get stressed like springs. And if you ever compress a spring, it pushes back, right? So that's what solids do. What happens is, wish this was a whiteboard. Should maybe get a little whiteboard to do this. What happens is the molecules get stressed down, and that's what provides the upward force to support everything. And that's where the normal force comes from. So yes, these objects can call it a normal force. Can a rope apply a force? Of course. You pull on something with a rope. You hang a tire swing. You have a swing hanging in your backyard from some chains. All right. We call this the tension force. Tension. And so rather than saying the force of the string on the object, we'll say Ft. But with all of these, it's like force of rope on object or force of chain on object. With all of these, you always have to remember where the force is coming from. All right? It's always an object acting on another object. All right? Always. Always one object acting on another object. That's the way this always goes. Okay? Never is any different. And then the last one there, the acceleration of an object is 0, are there no forces acting on it? Well, you go back to this. This object's acceleration is 0. It's just sitting there. But there's forces acting on it. They're balanced. The whole point is, going back to Newton's second law, Newton's first law, if the forces are balanced, its motion will stay constant. If they're unbalanced, the motion will change. So constant motion versus changing motion is no acceleration versus having acceleration. Constant velocity versus changing velocity. So forces are balanced, that means the velocity is constant. And that could be a constant velocity of 0. All right, so let's go look at the back here. Now we started this in class, but again, those of you full remote, Just want to talk a little bit about this so you are all on the same page. All right. Draw and label a quantitative force diagram for each block using equality marks on the vector. So I'm starting to get bleed through here. Let me get these papers from underneath here. Should really get a small whiteboard. That'd be much better and more environmentally friendly. All right. So I'll draw block A first. So I always like to work my way down here. So block A is force diagram. All right, that dot represents block A. We always have force of gravity, FGA, I'm going to call it. It's good, we're not writing the full object agent notation out, but this is the force of Earth on block A. You cannot lose sight of that. That's so important. So FGA. All right, then what's holding B up? What's holding A up? Well, B is holding A up, so it must be the same. FG, or not FG, FB A, I'm going to call it. Force of B on A. So when it's objects interacting that are labeled like this, A and B, I don't like to call it a normal force because there's going to be a normal force down here and I don't want to confuse them. It's force of B on A. Force of block B on block A is what's holding block A up. Now it says to make this quantitative. All right. Well, I can calculate FG on A. All right. So remember, FG equals mg, right? So FGA is MA, which is 0.1 kilograms, times G, which is about 9.8 newtons per kilogram. FGA is about 1 newton, all right? You can, mg, 0.1 times 9.8, you can round that to about 10, all right? So 0.1 times 10 is about 1. So FGA is actually, we're going to call it -1 because it's pointing down. It's up to you to assign the sign on the gravity. All right. Now, I don't have any way to calculate FBA, but I know it has to be +1 because they have to be balanced. This thing's not accelerating. Oh, great. Awesome. Well, let's draw the force diagram for B now. All right. So FGB is going down. Force of gravity on B. I made it smaller because the mass of B is smaller. So that equals 0.0, 5 kilograms times G, which is about 10 newtons per kilogram. So I like to just calculate it right away. And I'm going to have to make it negative. It's up to you to make it negative. So it's negative 0.5 newtons. You have to make it negative. All right. So then what else do I have acting on B? Well, A is touching it, right? A is also pushing down on B. FBA, and it pushes down on FAB, force of A on B, and that has to be equal and opposite to FBA. This is an action-reaction pair, force of B on A and force of A on B. So that's Newton's third law. For every force acting on an object, there's a force acting on another object. So even this force, FGA, well, that's the force of Earth on A. The action-reaction pair to that would be, partner to that would be force of A on Earth, which does also exist. This is not an action-reaction pair. These two forces do not need to be equal to each other. The force of B on A, right, if the table was all of a sudden, the legs were to break and this thing would start to accelerate down, that could be smaller than this. Or if someone was to lift the table up, FBA could be bigger than FGA. These do not need to be equal. These are literally the same force. FBA and FAB are literally the same contact force. -1 Newton. All right, so then I'm going to call the force supporting B, I'm going to call that the normal force. FN on B, FNB I'll call it. That's going to have to be equal to, well, everything's got to be balanced, so total pulling up has to equal total pulling down. It's going to be plus 1.5 newtons. All right? Very cool. This is balancing forces, balancing force diagrams. All right, pretty straightforward stuff, but first time you're kind of seeing it. All right, I'm shortening the wording down. All right, let's move on to the next problems. How does the force A exert on block B compared to the force B exerts on A? Draw and label a force diagram for each block, including the quality marks on the vector. So the force block A exerts on block B has to be equal to the force that block B exerts on block A. All right, they have to be equal and opposite. So let's draw A first. Well, actually, I'm going to draw B first, so it's in similar arrangement to what's on the paper. So forces acting on B, we have up and down forces are going to be balanced. This is FGB. That would be about 1 Newton again. Fn on B would also be about 1 Newton. I don't need to label those. It doesn't say to. It doesn't say anything about friction. So I'm going to pretend it's constant velocity. See that? So let's talk about that for a second. This is the force of A on B. Force of A on B. Now, constant velocity means the forces must be balanced. So there must be a force resisting this motion, balancing out the force of A on B. What would that force be? It must be a force of friction. Force of friction on B. All right, must be a force of friction. Otherwise, if you were to push this, it would accelerate. Since it's a constant velocity in this diagram, then it must be a force of friction acting on B right here, right on this bottom surface. Right, as you push, and friction is also a responsive force. It responds against whatever force is being applied, essentially. Responds against the direction of motion. All right, so block A. All right, FGA, I'm going to make proportional. So equality marks, you can make those if you want. These two have to be equal. Up and down have to be equal. I'm not a big stickler about those. If you draw the vectors the same length, then that should be good. So force of gravity on A, normal force acting on A, those have to balance each other out. All right. Then I've got, let's see, I've got the hand pushing A. Active hand. I guess hand on A, I suppose I should say. And then I gotta draw in some other stuff. So force of B on A is going to go to the right. And I can tell I've already messed up my force diagram here. This hand on A force is going to have to be a lot bigger because I also have friction acting on A, right? Resisting motion. So force of friction on A. If I have friction on B, I probably ought to have some friction on A. Now, the problem here is force of friction on A should be less than B, which we'll learn about later on because it's lighter. I drew this force of the hand too short. The force of the hand has to add, these two have to add up to it, right? So the force of the hand's got to be something like pretty darn big, right, to make it equal to some of these two. But again, I'm not going to be strict sticklers about that. And I can't really put equality marks on this because it's these two adding up to equal this one long one. So I'm going to leave it like that. All right, and then the last one I'll leave for you to do. It's very similar to the last one. It's just that the hand is going to be pushing to the right. And since it's moving to the right, oh, wait a minute, it doesn't say anything about friction. It says a constant acceleration. So eliminate friction for this one. Eliminate friction for this one. That's a little tricky. All right, and do your best on that one. And check the solutions, and we'll see how it goes. All right, have a good one.